Let's have a round of applause for Ricky. He leads the team at building Preform, the software that makes Formlabs 3D printers approachable to anyone. So let's hear about managing risk. A little clap of our hands.
Thank you. Now, can everybody hear me all right? Awesome. Let me just get this into the right presentation mode. All right, perfect. So, like they said, I'm Ricky, and I want to talk to you a little bit about managing risk and how we do this at Formlabs. So, just to start off, just a quick show of hands. Raise your hand if you have ever made a plan before and something has gone terribly, horribly wrong. Me too. I'll give an example. So one of my hobbies is woodworking, specifically designing and building musical instruments. So this is a fretboard from a guitar I was building a while ago. And when you're building a guitar, this is one of the critical components where everything needs to be measured just right. Essentially, all the frets on the guitar need to be parallel to each other. They need to be perpendicular to the direction of the fretboard, so they all need to be at these perfect 90-degree angles. And everything needs to be spaced just right so that when you're playing a chord or playing along, that everything's in tune with each other, everything sounds like it should. So for this fretboard, I was trying some new processes, and there is a rule we have in woodworking: measure twice, cut once. Now this is important because any cut you make in wood is not a reversible process, especially if you want to be able to let the final wood grain show through. So you'll see this fretboard here, it's a really red, really brilliant colored piece of wood. And anything I did to that, like if I have to do it again, that would be very, very bad for the project. So I was introducing some new tools here. This was the second guitar I'd ever made. So this is a miter box. It's a tool in woodworking to make sure that every one of these cuts you make on a board is at a perfect 90-degree angle. So effectively, it has one job. And in part of my process, and in being new to this at the time, I had not tested or validated that it did this one job well, and I trusted that this would go fine. So I expected that when making these cuts, I would get this perfect 90-degree angle, and sadly, that was not the case. I ended up ruining this piece of wood. Fortunately, I had another blank that I could try on, but every cut that I had eyeballed and looked perfect at first glance was actually 1 degree off, and that meant that I couldn't salvage this fingerboard. I was able to make another one, but for this stage in the process and for this kind of wood that's very hard to get, I should have validated this much more, and I should have assumed that there was a much higher risk in this process. So with woodworking, unlike with software development, you cannot easily undo your changes. This was something I had to deal with. I had to bring another board in the project because of it, and I had to write this one off as a loss. So you may be asking, why am I talking about this? So my background, I work with emerging technologies where things are typically very early in development, and there is a lot of risk to any software project you take on. So in the business world, this is what's known as the technology adoption curve. The theory behind it is with any new technology or any new product, that there's going to be a very small number of people adopting it at first. It's not going to be useful for most people. And then over its life, it will eventually, through its life cycle, be adopted in a bell curve. So in the middle of its life, when it's solving the most problems, that's when most people will jump on the bandwagon. And then finally, the people at the end will start to catch up and start to use this. So with many emerging technologies, at first we have this section here, the innovators or the tech enthusiasts. This is also sometimes called the Kickstarter era, where something new will come up on Kickstarter, there'll be a new product. So not all the loose ends are worked out, everything doesn't work perfectly, but it's a brand new technology and a new concept that shows a lot of promise for the people that are excited about it. And after that, you have the early adopters. This is when things typically get turned into a full product. There's more going on with it, more of the quirks have been ironed out, and it's more applicable to a lot of people. So it's solving problems, but still for a smaller population. And after this, there's this gap that can be very hard for technology to overcome. Getting over this is called crossing the chasm. We won't get into that too much here, But the reason I bring it up is that this is where a lot of risk has to get played down and a lot of things need to get figured out to be able to really help a new technology take off. I personally really like to work in this area. This is where there's a lot of really interesting problems, interesting learning to do, interesting technologies to start playing with, and it's a good intersection between like technical problem solving and really discovering what something can do and how it can make an impact. So again, why am I talking about this? How does this relate to a software development conference? So I work at a company called Formlabs. We are a company that makes 3D printers and generally the tools to help anybody make anything. My role specifically, I'm a product engineering lead, which is basically 50% product management and 50% technical lead. So I'm sitting between the engineering, product management, and design teams to help figure out how we can solve more problems with our products and how we can get them out to more people. So our company, these are the 3D printers that we make. These two on the outside, the Form 3L and the Form 3 Plus, these are SLA resin printers or stereolithography. They work on liquid resin, and this is how our company started. We were actually a Kickstarter company back 10 to 11 years ago, proving one of these new concepts out, and this is the third generation of these products. Now, a lot of the risks I'll talk about focus on some of the newer things we've been working on, but these are things we've essentially been doing for the entire course of our company. This printer in the center is Fuse 1. This is a new technology that we just released at the start of 2021, and it's a different printing technology. It uses a powder instead of a liquid resin to make objects, and I'll talk a little bit more about that process in a minute. So our big advantage as one of these 3D printer companies is we really have a fully vertically integrated process. This means that we make the hardware, the materials, and the software ecosystem to bind everything together. And that software ecosystem is what I want to talk more about today. So for our main printers, they create parts that have to adhere to the build platform somehow. And one of our software projects that we took on was actually making this experience as painless as possible. So just to give context to how these work, this is how a part typically comes off the printer. There will be a raft with supports attached. And then as the person using these parts, you break these off, and then there may be minimal sanding to do. But a lot of our software engineers have actually spent a lot of time tuning this to the point where you don't need a lot of manual labor to get something useful. So what kind of software makes this possible? So we have 3 software components in our stack. There is a slicing software, which is the application that makes it possible to go from a digital model to something that the printer can understand. That's called Freeform, and that is where those support structures get generated and where you can generally manipulate these objects. There is Dashboard, which is the web service that monitors your print as you go. That's the thing that makes sure that if there are any errors, you know about it. If you have to do anything, you're always in the loop. And you know when things are going to finish, so you can get as much use out of these as possible. And then there is the embedded system, where we spend a lot of time making this very intuitive and giving the user any information that they need to be able to use these printers effectively. So with our development process, we believe that these programs should be very tightly coupled. And we have our developers really owning entire problems and moving between these parts of the stack as needed. So we'd much rather have people own the whole problem they're solving and be able to understand everything from end to end and not just work on one of these projects. So the challenge we run into, and I think the challenge a lot of technology companies run into as they grow, is it's very tempting from the management perspective, either as an engineering manager or as somebody else in a different role, to choose a development pattern or a development process that is supposed to get the most efficiency out of our teams, to make sure that we're able to see clearly how far things are in the process, and we're able to check in, we're able to have visibility. And as we've grown, we've noticed that there are a few different things to borrow from each of these. Each of these frameworks has its own merits, they have their own advocates, and they are very relevant for certain types of problems. But if you follow one of them prescriptively, it's very easy to fall into a rabbit hole or to start fitting a square peg into a round hole. So when we approach projects, we think about it like this. This is Murphy's Law, and basically it states that anything that can go wrong will. I've been victim to this multiple times, but this is basically saying that when you start anything new, you need to assume that if there is a risk or if there's a big risk, you need to test that first to make sure that doesn't get in your way later. So really these software development projects, especially in emerging technology where there's more risk than a lot of other spaces, need to be structured so that you're addressing these risks first, and then after you address those, you can start to build things out and make them ready to actually ship. So I want to talk about how Formlabs has run this and how we've approached these different kinds of problems. Like I was saying, it's very rare that we work on the same thing multiple times in a row, and this problem space in 3D printing is very broad. So I'm going to talk about 3 very different kinds of projects. All of these processes were led by software engineers who really wanted to get the most out of the products and really make the most effective thing that they could. So there are other management sides to this and product management sides to this as well. But I really want to highlight the things that our engineers have done to make sure these things go smoothly and have impact. So the first project I want to talk about is 3D packing. Now this is a project that was actually done between our 3 offices in Budapest, Somerville, Massachusetts, and North Carolina. A lot of the stuff I'm going to talk about was actually developed here in the Budapest office by one of the software engineers leading this. And it's all in support of the Fuse 1 3D printer. So in 2021, we launched this printer and immediately discovered that there were a lot of unique problems to solve for this, and the way that people were going to use this technology is very different than the way people had used our other printers. So these printers are mostly focused on high throughput, and they are focused on end-use production, much larger batch operations than other 3D printers were. So the 3D packing problem is essentially trying to fit as many objects into as small of a space as possible. When we started looking into this, the first inspiration we found is a large industry built around bin packing, which is very popular in the shipping industry. It's essentially built to ensure that as you're shipping things across oceans and using shipping containers, you are filling up as much space as possible and really optimizing your costs. Now for shipping, this makes a lot of sense, but there is one key constraint that made it so that we had to approach the problem in a new way. In this problem, everything looks like a box. And in 3D printing, one of the value propositions of being able to make anything is that most of your parts don't look like boxes. Here's a sample build that we made on the Fuse 1. There are a lot of different types of parts in there. There are hinged containers, there are gears, there are bike pedals. I'm pretty sure there's even a very detailed lifelike crab model in the background somewhere. That was something people were printing a lot of at the time. But the point is that you can make anything with these, and a lot of the constraints that go into other research on this topic did not apply to our space. So we had to approach this fairly from the ground up. So when we started this, we asked ourselves, what are the risks of this project? What could go wrong? And the things we found were, essentially, the new algorithm would not get adequate results. The behavior people were doing before with Fuse 1 is a lot of people were essentially playing a giant game of 3D Tetris to fit everything into their build volume. So they were doing as much as they could. They were spending hours in front of the software, actually getting everything to fit right and pack down. And we needed to make sure that we could replace those results. And the other side of this, the new algorithm is too slow to be practical. Even though that process took hours, people were able to make a lot of small decisions during their layout of which models to include, which models to take out. And if our software ran too slowly, they would be waiting and waiting and waiting, and then they would have to make another decision and run everything again. So we couldn't have that happen. So the best way we figured out to mitigate these risks was actually to build a testing harness and measure the algorithms as we develop them over a large set of models. So you'll see here, this is one of the initial tests that we ran. We had our solution running with slight tweaks, and then we picked 3 softwares that were on the market to benchmark against. Now this is a functionality that was available in some professional grade software, normally in the tens of thousands of dollars a year category. And we thought it was very important for our customers to be able to have access to this to use their printer to its fullest extent. So we wanted to make this available for everybody within our free software. So our first benchmarks against this proved pretty conclusively we were not there. We had a lot of work to do, and through the models we tested, we knew there was a lot of improvement to make. So as we developed this, the first thing we did and the first thing we put a lot of effort into is actually making a test harness instead of the algorithm itself. So what we did was we gathered up as many printing scenes as we could, or things that would turn into print jobs, these groups of objects. And we randomly generated a bunch more, so we had on the order of 1,000 scenes to test with. And in this, we made this test harness so that every night, or however long we wanted to wait until we ran this next batch of tests, we could measure all the improvements that we'd made at that moment and clearly get feedback on how we were doing. And we could see, is this succeeding? Do we have more work to do? What do we need to optimize for? We could answer all of these questions with this data. Now we also use this to measure how much time this took. So with each of these runs, we saw that we were largely more successful than the benchmarks we were comparing against, but we were taking a longer time. So this actually helped us tune our results and optimize the problem space. to be able to make sure that we were delivering something that would work well for all customers. And after we shipped this product, we actually kept putting these metrics in, and we monitored the same things in the field. And this both showed us that it was a successful project. The risk management we did paid off. So people were using this, we had denser packed jobs, and we could monitor these in real time and see how they changed with other tweaks we did to the algorithm. Now, this also confirmed it was a large improvement, and we could also look through this data to see where to go next, like where there was still risk, where we still weren't meeting the mark for some customers. So this has been really successful, and the strategy that our developers came up with for that enabled the success of this project. So back before this and the life cycle of the same printer, this is another project I want to talk about, but it's on the user interface side of things. So a few years before that, when we were launching this Fuse 1 printer, we realized that we needed a UI for it. And we had experience in this. We had made other printers with touchscreen interfaces before, but this technology was so different and there were so many unique problems to it that we needed to approach this with fresh eyes. And we could use what we'd learned before, but we also needed a new way to solve these problems. So this is what it looks like to post-process a part created with Fuse. And this post-processing just means cleaning up the part so you can handle it after it's printed. Now, it looks a little bit like an archaeological dig, and that's because it feels a lot like an archaeological dig. Essentially, you have a large container of powder, and as the printer lays down powder inside, it controls the temperature just so that a laser can push certain parts of that powder over the melting point. And you end up with a very sensitive environment that creates very, very detailed parts. Now there's some excess powder to brush off after the fact and some post-processing needed, but this is a great way to get a lot of detail and to get really, really fine-grained dimensional accuracy. So designing a UI for this new type of printer, we had to work around that extremely sensitive process and also the other requirements needed to make this successful. So this is a new technology, but what problems does it create on the UI side? For one, you can't see what's happening inside the printer without the screen. So our other printers, the Form 3L and the Form 3 Plus, they have a transparent orange window on top that you can open at any time to see what's going on. You can make sure things are successful. You can make sure that if you need to replace any components, you can do that easily. But since this is a delicate temperature environment, you absolutely need to keep this sealed, and you cannot open the door, otherwise the print will stop. So that's a constraint we had to work around, and also we couldn't put a window into the printer, so we needed to both communicate what was going on inside and put enough information out that people had what they needed to be able to proceed. Also, you can't open the door, so we had to design a software component around both safety and accessibility. And adding material is not contained or controlled in any way. So with our other printers, we had a cartridge of liquid resin that you could just drop in the back and it would automatically dispense. With this new printer, you had cartridges that you could empty into the printer, but we didn't have as tight control over how that was dispensed or added to the machine. So there were a new class of problems to solve there. So we asked ourselves again, what are the risks? What will make this project go wrong? The first one is it will not be intuitive. Since this is such a complicated process and there are other things the user has to do, we were worried this would be a difficult product to use and that people wouldn't be able to get as much out of it. And our second risk was that the UI would actually impact the print results, that somebody would forget to do something ahead of time that they needed to do for the printer, or that something would happen, they would accidentally open the door, and then they would waste tens of hours. So how do we mitigate this risk? We looked outside of the typical software development process for this and into the design world to a process called a design brief. Now, this is something that designers are very familiar with. It's good for discovery processes and for finding out a lot more about a problem when you don't know who's going to use it. But it's essentially a way to collect all of your requirements, the people you're designing for, the scenarios you want to make sure work well, and the principles you want to use to design this project, and get them all in one space, talk with them with as many people in the company as possible, and improve your understanding of what you're building. So this is one of the earliest things we did in this UI project. We got these personas down of people that might find this project valuable, got the objective above, got these scenarios, identified the principles of the team that we were all designing all parts of the project around. And then this gives us what we need to be able to start developing and start trying out new ideas. The other big thing we did was just getting it out there and getting people to use it. So the best way to find high-level usability issues is just to use the product as much as possible in every stage of development. So for us, this meant running the UI on prototype printers that we were creating and testing it relentlessly. What this meant in practice was that I, at the time, was actually running around our headquarters when people were using this, and I was badgering people for feedback whenever I saw people get confused. And at this point, this was one of our prototype printers. We were naming them all after birds at that point, so this one is named Pelican. This was early development, and we hadn't finalized a lot of these systems. We hadn't finalized a lot of UI decisions. This was one of the first versions of the UI that we changed a lot, and it really helped us make sure that once we got it out to customers, it was the best thing it could be. There was another part of this on the more technical side that also helped us adapt too, and that's architecting for learning. So when you're making a new software project, there's always a temptation to make it as robust as possible, to make it just as stable as you can, to try to identify every scenario. And we approached this a different way. Instead, we put in the simplest possible architecture we could that would allow us to try new ideas, to learn more, to adapt quickly. And we recognized there would be trade-offs later on, but that learning was the most valuable thing, and that was the biggest risk. So we built around that. So our approach was essentially a stack of independent stack views. In the UI sense, this means there are multiple parallel screens running on top of each other at all times. Some of them aren't showing anything, some of them are showing some contents on part of the screen. But this let us create new components without having to introduce a lot of boilerplate, without having to introduce special logic around some scenarios. And it had trade-offs. We did have to re-architect certain parts of this later on, but it helped us learn as efficiently as possible, and it still helped us get this velocity. So when Fuse came out, this is actually one of the products that when it launched, it had the highest customer satisfaction of all of our other printers. And we still see people interacting with the UI. We see improvements, but we see that overall we've created a great user experience with this product. So the last problem I want to talk about is more on the performance tuning side, and this is swab production. So at the start of the pandemic, as I'm sure everybody remembers, the world was low on supplies. We needed to react fast. At this point, the 3D printing industry came together and essentially acted as a giant, massive manufacturing network to produce personal protective equipment and other things we needed for testing and safety. So our contribution to this was actually working with USF Health and Northwell Health, and we were able to use some of our biocompatible printing materials to actually create real testing equipment that could be used to actually create these full test kits and get them out wherever they could be manufactured. So what this ended up as is we created a design where we could fit 324 of these objects on a single build platform, which is great. It unlocked a lot of production, but it also meant that we had a new problem to solve in our software. Essentially, we were not designed for production use cases at the time. The 3D printing industry at that point was much more about mass customization and small runs of customized objects than it was about full-scale production. So the thing we ran into very quickly is with the detail of these models, every one of our algorithms had to go through so many more vertices, and the order of complexity was just so much greater than it was before. And we had to do this 324 times. This meant that when somebody loaded up our application, they actually had to wait more than a minute to be able to do anything else. This wasn't acceptable and was the biggest risk in this project at that time. So when we inventoried our risk, this was the main one, where our software was not constructed for this. And looking at the different parts of the workflow, we were really focused on which parts of this process people actually need to be at their computer for, and what will actually keep them waiting and keep them from doing other things that are also urgently needed. So what we identified was an algorithm called printability. So this algorithm, this is an example preform job here. This is what it looks like when you open this job for printing. And as you'll see, there is a model list on the right side that lists 324 copies of the same thing. And when we were computing whether or not this could be printed safely without falling off the build platform or without failures, we essentially go into a process where we're computing printability. We do this on a per model basis, so we essentially spawn 324 of these threads, put them into a thread pool, and then wait until they all finish for that end result. Now we thought about multiple ways to do this. We could just check for duplicates in the scene, though that would introduce additional architectural complexity that might be hard to recover from. So we wanted to look at different approaches to this. We looked through the C++ standard libraries. We looked through other libraries in our project. There wasn't a good way to do it at the time. So after we identified this as the bottleneck, our team went to work and actually checked out some of the open source libraries we're using and tried to see if we could fix it ourselves. So we identified an improvement to Intel's 1TBB library. That's the one API threading building blocks. And we made a modification that allowed us to turn this problem into this. So essentially computing the printability of one swab and then having other threads that were waiting for that to finish. And we could do this both in parallel and without having to do these specific checks. So this saved us a lot of time. The end time we had to spend waiting for that printability to run went from 80 seconds to less than 2. So it's a dramatic difference and really unblocked people using this. And then this change we made to 1TBB, we also continued to work with Intel to refine this, and were later able to get it back into the open source world in November of 2021. So these are 3 examples that show some of the projects we work on at Formlabs. Each one of these has required us to really step back and take a fresh look at what could go wrong, what the risks were, how we wanted to run this project. So we have this very broad domain. There's a lot of exciting problems, but there's a lot of things where we are just not familiar enough to make a call ahead of time, and we really have to step back and take this look at it. So it's a fun industry to be in. We get to work with a lot of cool technology. We get to solve a lot of real-world problems, and we also get to print a lot of fun stuff. And we're constantly pushing the boundaries of this industry and finding new things we can do with this platform. So I hope that hearing these stories about what we've done at Formlabs and the different things that we've solved over time is helpful to you. I hope this helps you be able to form a process around your next development project where you can look at these risks and make sure you're tackling those first. And when in doubt, start with Murphy's Law. Anything that can go wrong will. So with this mindset, you can tackle the biggest risks first, learn as much as possible, and get things out the door with confidence. So thanks for listening. We've got our booth over there, and we'll be at the networking event tonight for any other questions. But now I think we have the Q&A section also. Thank you.
Hello. All right, you can hear me. Okay, cool. It's very funny. I hear myself all the time now. I'm getting used to it. Okay. So, how was it for you hearing yourself? Are you hearing yourself now?
I am, yeah. It's definitely not something I'm used to, I'll say that.
It is very odd. All right, so if you don't know, go to Slido. We're going to read some questions out loud here, and this is your chance to ask Ricky any questions around managing risk. So we have our first question here. How was 3D printing the best solution for swab printing?
And so 3D printing was the best solution for swab printing at that time for certain people, but not others. So really what we wanted to do, we were not assuming that everybody was going to start using a 3D printer to print swabs instead of other manufacturing methods, but we wanted to make sure that people had as many different ways as possible to produce these. So it's not necessarily that it is the right tool for the job. It's not that 3D printers are sometimes the best job for certain geometries or best solution for certain geometries. But this was really just intended to make sure that if people had this tool that was capable of producing these results, that we unlocked that capability and we weren't holding people back.
Very nice. I like this next question. I was about to ask you off the stage, but can we see a finished guitar?
So that one's actually still in progress. I can show you another one that I've made.
Would you like to see it? The hands. Oh, wow. Look, you got the crowd.
I'll have to find that picture. Okay.
All right. So maybe after the talk?
After the talk,
okay,
yeah.
Perfect. All right, cool. So now you got a promise from him. Find him. See that guitar. All right. There are very interesting stories about Formlabs. What is your advice about how to manage risk in general? Is there a general process you're using?
I think the closest to the general process I can really say is when we start any project, this is typically the first thing we talk about. We'll make a document that shows what we want to accomplish. We'll talk about what the feature is. And then from there, we'll be able to say, okay, what is the biggest thing or the biggest assumption that we're making that this will be valuable? And if we can inventory that list of assumptions that we're making, like this will work, this will be a beneficial thing, then we can start to look at which of those presents the biggest risk to our project. And this is generally something there's not really a risk score that I can recommend. This is often just a conversation with the people working on it and using people's intuition. But having some structure to this and going through that list of assumptions first is generally what I would recommend as a starting point.
Got it. And I think this next question is somewhat related. So has it ever happened to you that risk came up which you did not think at the start?
Almost always.
Always.
Yeah, so that's an important part of just software development too. Again, with the guitar example, if something comes up that we don't anticipate, there's a much higher cost. But with software development, if you do find a risk later on, it's very iterative. You have this opportunity to fix things quickly. So I think that, identifying those risks at the start is the best way to ensure success. But even if you don't take the time to do that, even if you miss something, there's still always opportunity to just build that in and fix that later.
So I guess that also answered the question to how would you react. So you would add it to the iterative process, the next iteration, you basically start addressing those things over time.
Exactly.
Cool. Next question, how a typical development flow looks like from the UX to the embedded system.
So from the UX standpoint, we typically try to figure out the problem that we're solving first. There will be some design work to just figure out the space of the problem, what we ultimately want to do. We may make some mock-ups, we may make some wireframes, but there's always a temptation to get everything as perfect as possible before you start development. And every time we have done that, we get things to a perfect point, we start developing something, and then we realize it wasn't the perfect point after all. So typically, even on the embedded system, we will make these prototypes. We will get an idea of generally what we want. We'll start building the scaffolding for it. We'll start putting the low-level parts in place. And then we'll build up with that combination of real-time feedback and that additional thinking from our designers.
Nice. That sounds pretty cool. So do you have any more questions? This is the Slido link. If you're having an opportunity, just something that came up to mind, we're happy to answer them. If not, Ricky, are you going to be around? I guess you said that you're going to be in the booths as well?
I'm going to be in and out at the booth, and then also at our networking night tonight. I'll be around. Happy to answer any questions. Happy to show people the guitar if you're interested in it.
All right, so please a hand of applause for Ricky coming up and sharing how to manage risks.
Thanks
again for being here.